diffusive surface finishes. The case study I'm going to talk about now is the diffusive panel design for the Glasshouse Theatre. Glasshouse Theatre is a 500-seat multi-purpose theatre designed to be used for any purpose, including school assemblies, musicals, drama productions, and rock music. This theatre had a variable acoustic. What that means is it had deployable acoustic banners that changed the reverberation time according to the use of the space. And in this case, the reverberation time could be changed from 1.1 seconds, which is suitable for drama performances, to 1.4 seconds, which is more suitable for musical performances. One of the attributes of the theatre is that the rear wall of the theatre at low and high level, you can see on the left-hand side here on that picture, and then on the right-hand side here, a close-up of the bottom or the lower level rear wall, was a concave shape, which if left untreated would give rise to focused reflections of sound back to the audience and back to the stage area, which might be very distracting to occupants of the theatre. So it was necessary to treat these rear walls of the theatre to provide scattering of sound or diffusion of sound to avoid these discrete reflections arriving late back towards the audience and the stage area. What we did very early on in the process was ask the architect to provide a scale model of the rear wall of the theatre. The concept design put forward by the architect involved twisted panels through the diagonal axis of each panel. So what we decided to do was use a laser pointer to scan across a scale model of these diffusive panels to try and see where we might get problematic reflections of sound back towards the audience. The reason why we built a scale model is that computer modeling is still not advanced enough to accurately predict diffusion or scattering of sound in theatres at the design stage. So it was much easier to build a scale model with reflective silver paper on the rear wall of the model and scan a laser pointer across these panels to see where we got these reflections of sound. So we've got two camera angles of the testing that we did. On the left-hand side here, we have a stage location. So we have a laser pointer located at the stage pointing towards the rear wall. By scanning the laser pointer across this scale model, we would see where we would get reflections of sound, which would be seen by red dots, back towards the audience and back towards the stage area. The other camera angle we have here is looking back towards the stage, so you can see when we scan the laser pointer across where we would get these problematic reflections of sound back towards the stage area. So I'm going to play you these two videos and you can see where we get the red dots or the reflections of sound back towards the stage area and the audience area. So every time you see a red dot coming back, that's where we get a problematic reflection of sound in the auditorium. So the aim here is to try and eliminate these spots in the panels where we're getting the reflections back into the audience chamber. So by doing this scanning, we were able to determine the exact part of the panel here shown on the right-hand side as a drawing, as one of the architectural drawings. The hatched area in red here is where we were getting these problematic reflections of sound reflecting back towards the audience and back towards the performers. So instead of putting absorptive material on this patch of the panel, we wanted to keep the reverberance or the reverberation time as we designed. So what we wanted to do was redirect or scatter the sound in a random direction to keep the sound energy in the space, keep the reverberance, but avoid those problematic late reflections of sound. So here's the design we came up with. Here's some of the panels that were set up for prototype testing. On the left-hand side here, you can see we have this Morse code style architectural pattern put over the panels. These are quite shallow wells and slots in the panel that provide scattering of sound at very high frequencies, where the wavelengths are very small. So by having shallow depths of articulation on the panels, we can get high frequency scattering of sound. To achieve low frequency scattering of sound, we needed protrusions or articulation that was deeper and more in line with the wavelengths of sound that we're trying to scatter. So you can see on the right-hand side here, I've done a close-up of the panel, and you can see what we have here are these protruding elements coming out of the panels along the axis of the panel. These protrusions or dowels provided the mid to low frequency diffusion or scattering that we needed to avoid those reflections in the performance space. Also, the natural twist of the panels across the diagonal axis here provided very low frequency diffusion. So where the wavelengths are the order of a meter or higher, the natural twist of the panels provided that natural scattering.